Okay, welcome to this course on stereochemistry. This is a basic subject branch of chemistry, and it primarily focuses on the fundamental aspects of this topic. Now, stereochemistry, like any other branch of subdisciplines, this has also emerged from a historical perspective. This is a very interesting concept in the subject of chemistry, which is applicable to not only to chemistry, higher level chemistry, but also to various other branches of sciences like biology and medicine in particular. Why this subject is so important? Because of many reasons, but one primary reason is that the world that we are living in today is a chiral world. What does it mean? That means it is made up of systems which have a handedness. Handedness means that if I see the two hands, these two hands, one is they look almost the same, but they are not same. You cannot really superimpose, you cannot say that they are the same hands, because you cannot superimpose one hand on top of each other, and that is primarily because of the geometry and the way the fingers are aligned. Similar things happen in the molecular world, and as I said, we live in a chiral world, and that means that all the living systems that are there, they are made up of molecules which exhibit this type of handedness. Now, stereochemistry is the subject which deals with the property of the molecule in three-dimensional space. Chemistry first of all developed as the function and reactivity and structure of molecules, but purely on a two-dimensional plane. That means, the chemistry what was known earlier in earlier days was two-dimensional chemistry. That means, people looked at molecules from a two-dimensional aspect. But since this is the first class of stereochemistry, so I thought that I will first show you that I will introduce the course instructor, which is myself, Professor Amit Bashak, and my teaching assistants. You can see the names: Arundhati Mondal, Ishani Das and Monisha Singho, and they will help in answering your queries, and they will also upload the questions and other teaching materials, and finally, they will also try to dispel any doubt that you have while going through this course. Now, the problem of stereochemistry lies with the visualization of molecules in three-dimensional space, because you do not have the luxury of having a molecular model in your hand when you sit in an examination hall. What you have to do, if you have a problem, you have to visualize it in the three-dimensional space, and then try to figure out that what would be the perfect geometry, how does it interact with other systems. So, that was the most difficult part of stereochemistry, that is the visualization of molecules in three-dimensional space. What is the difference between this two-dimensional chemistry I was talking about? That is, before that, let me show you what are the different modules that are there in this course. These are already put in the web, and I think you can go through these 8 modules that are orchestrated in such a fashion that slowly you learn how to draw the three-dimensional structures, and then try to analyze their interrelationship, and then finally, we will come to the reactivity of these molecules and the reactions involving with these molecules. So, basically this is a very fundamental undergraduate course at the first year, second year BSc level, and I hope that initially there may be some difficulty in visualization and conceptualization of these 3D molecules, but later on I am confident that if you go through this course, you will also feel confident like me in uh, in answering or in conceptualizing the reactivity of molecules which can exhibit 3-dimensional geometry. So, what is this again I come back to the definition of stereochemistry, that means it is what I am telling, that it is a function, it is a function of 3-dimensional, a function of a molecule in 3-dimensional space. I can clarify it little bit with this slide, that if you take benzaldehyde versus orthomethoxybenzaldehyde, you know that this carbonyl group is susceptible to nucleophilic addition because of the electrophilicity of this carbon. But this is these two molecules, although they react with a nucleophile like X minus, but their reactivity is little bit different, their rate of reaction will be different because of of the electronic effect of this methoxy group versus the hydrogen. What are these electronic effects? That is the minus I and plus R. So, here the reactivity difference comes from the electronic effects and not any stereochemical effect. That means, what I am saying, it is not that the methoxy is pointing in this direction and that is the cause of difference in reactivity of this carbonyl versus the other carbonyl. While if you take the completely reduced system of these two molecules, especially this one. So, if you reduce it, all the double bonds are reduced. So, you get what is called a cyclohexane system. And now, when you reduce, you have a very interesting situation, that this aldehyde may be aligned on the same face as the methoxy group, or the aldehyde may be aligned in the opposite face of the methoxy group. And because of this relationship, geometrical relationship, now the reactivity of these carbonyls will be different, and this difference now comes from the as a result of the different geometrical relationship between these methoxy and the aldehyde. In earlier case, again I repeat, this methoxy is exerting electronic effects compared to the hydrogen, and that is the reason for the difference in reactivity. So, the reactivity of this aldehyde now is dependent on the steric disposition, that means the 3-dimensional disposition of the methoxy group in space in relation to the aldehyde. So, that is a very simplified way of describing what is stereochemistry. Now, this subject did not evolve from a very rational approach like many other subjects. In medicine, what happens? Many of the medicines are discovered by chance, and then people know how these medicines worked and then developed newer medicines. Similarly, stereochemistry also developed it's developed by chance, by trial and error, by serendipitous discovery, and then people finally come out and explain what was happening, that what was the serendipitous observation, why is it happening. So, I will tell you the historical perspective of the development of this subject. Now, it all started with the property of light, which we know that it is electromagnetic, it is an electromagnetic wave. So, there are two vectors, an electrical vector, electrical wave, and a magnetic vector, a magnetic wave, and both are perpendicular to each other. Now, if you consider only the electric vector, so what happens in normal light, the vibrations, the electrical wave vibrations are taking place in all directions, that is possible around a point. That means, if I take this is the light the light passing from here to there, then the wave actually the wave is taking place in every possible plane, in every possible direction. So, basically it encompasses the whole 360 degree around this axis of migration of the light. That is the normal light. Now, in the 17th century, this Dutch astronomer Huygens, he discovered what is called plane polarized light. That means what I was telling earlier, that the wave was vibrating in all possible direction, that is the normal light, but when it passes through a special type of glass which is made up of some crystals, what happens? It allows only the vibration which is occurring in a particular plane, and then the light that comes out, all the vibrations are taking place in a particular plane, and that is what is called plane polarized light. In this case, because I am showing it in the horizontal direction, so that will be called horizontally polarized, but actually these are what are called either linearly polarized light, or for you as the beginner you should call it as plane polarized light, and the plane in which the vibrations are taking place is called the plane of polarization. Okay. As I said again, this is what is the plate, the kind of a crystal. It is made up of a crystal like crystal of calcium carbonate, which is known as calcite. They have this special property, not all crystals will do this. So, this plane polarized light, if you take another crystal which allows, which will also can produce this plane polarized light, but what happens if you now have this crystal or this plate aligned in such a direction that it will have the plane of polarization perpendicular to the plane of polarization that this crystal is generating. So, in that case what happens? This will completely block the propagation of the light on the right side. On the other hand, if you rotate this and ultimately by 90 degree, then what happens? The axis of polarization will become aligned to the axis of polarization of this plate, and then the light will come out. So, by these two plates you can actually analyze whether if you put a molecule here in between these, the light going from here to there, then what happens? If you think that the plane of polarization is rotated, then the way to do it, that whether there is any rotation or not, then you have to rotate this plate and then find out whether light is coming out or not. And so, it all started with the plane of polarization, plane polarized light, but then people were interested in seeing that how the molecules behave when plane polarized light passes through the molecule in a solution or in the liquid state. And very interestingly, they found that suppose this is a solution containing a sample x, a molecule x, and you produce plane polarized light by shining a bulb and putting a polarizer. This is, by the way, is called the polarizer. So, it will produce the plane polarized light, and suppose the vibrations are taking place in a vertical direction. So, now when it goes through the solution, if the solution does not change the plane of polarization, so the plane of polarization remains vertical. And if you put the other plate here, which is now called an analyzer, because you are analyzing whether there is any perturbation in the plane of polarization of this light. So, by the analysis, by this analyzer, you can now check whether there is any rotation in the plane of polarization while passing through the solution of the sample x. So, people started doing all sorts of experiments like with using different types of molecules, and what they found, that there are some molecules which rotate this plane of polarization either clockwise or in anti-clockwise fashion, and there are some molecules which do not. So, if it rotates, suppose this is an example where the plane of polarization is getting rotated in a clockwise direction, and how do you know? You rotate the analyzer, so that the axis becomes aligned to the rotated plane of polarization. Now, you can see the light coming out from this. So, by the amount of rotation that is needed to see the light coming out, that will be the amount of rotation that has occurred while the light is going through the solution. Okay. So, this was known, or this was shown by Biot, by a French scientist who discovered this phenomenon, that there are some molecules where if you pass the plane polarized light, that undergoes rotation, that means the plane of polarization undergoes a rotation, and then you can see the amount of rotation, and that is characteristic of the sample. But as I told you, this does not happen with all compounds. There are some particular compounds which has this typical property, and he called the rotation of this plane polarized light as the molecules are showing optical activity, and these molecules he called optically active molecules. The reason for this rotation of plane of polarization was not known at that time. Then what happened? After this event, then Louis Pasteur, the famous again French chemist, he came into the picture. So, what he did, see, at that time this molecule was known, this was called tartaric acid. It was obtained from various sources, like it can be obtained from fermentation of grape juice. So, this tartaric acid he collected, and then he did a crystallization of this tartaric acid, which was called at that time racemic acid. This tartaric acid obtained from grape juice fermentation was called racemic acid, and this racemic acid he crystallized it as the sodium ammonium salt, because it is a dicarboxylic acid. So, one is sodium, one hydrogen is replaced by sodium, and the other salt is the ammonium. So, it is a sodium ammonium salt, and then he crystallized it, and what he noticed that there were two kinds of crystals that were obtained, and he using a microscope he could separate these two kinds of crystals, and then he could find that this one set of crystals is the perfect mirror image of the other crystal. And then with these separated crystals he analyzed them, that what is the effect on the plane polarized light when it passes through these crystals, but the crystals are in solution now. So, basically racemic tartaric acid was divided into two sets of crystals. These crystals were mirror images of each other, and then when light passes through these crystals, he found that one set of crystals is rotating the light in a clockwise direction, the other set of crystals which are in solution, they are rotating the light in the other, in the anti-clockwise direction. Okay. So, that formed the basis that okay. So, basically you have the same molecule tartaric acid in two dimensional chemistry, this looked to be only one compound, but because they have different rotation power, rotatory power. So, they cannot be the same molecule. So, the molecule which looks the same in two dimensional geometry, now Pasteur has shown that actually they can be consisting of two different sets of molecules. So, that actually is the beginning of the three dimensional chemistry, which is called now the stereochemistry. So, this is he laid the foundation of stereochemistry. But the question is why, means how can you really explain this type of phenomena, that where you have the same formula, molecular formula, same type of connectivity, but you can have two systems generated out of that. Okay. But before that, Pasteur actually did another experiment. See, apart from racemic acid, which can be separated into two sets of crystals, he also studied another form of tartaric acid. He found another form of tartaric acid, the same molecular formula, same constitution, that means same type of atoms are attached to the similar type of atoms. And then he found that this tartaric acid, which was called mesotartaric acid, he failed to separate it into two isomers. And then he found that this does not also rotate the plane of plane polarized light. So, this is again different from the earlier racemic acid that he used, that we obtained from the grapefruit juice. So, now we have three types of tartaric acid. One is this mesotartaric acid, which cannot be separated into any different crystalline forms. That means, it is basically it is a one compound, single compound. And on the other hand, you have this tartaric acid, which was obtained from grapefruit juice. At that time, it was called racemic acid. It consists of two types of tartaric acid. One was because one was rotating in the clockwise direction. So, that was called dextrotartaric acid, and the other one is the levotartaric acid, because it was rotating the light in the other direction, that means counterclockwise or anti-clockwise direction. However, Pasteur could not explain why this phenomena is happening. That means, the molecule having the same molecular formula, same constitution, but how can it exist in three different forms? In 1874, Van 't Hoff and Lowell, they proposed that this is because of the existence of carbon in tartaric acid, where the carbon is attached to four different groups. Again, I just go back to the previous slide. If you consider the tartaric acid structure, you see there is a carbon. Usually, we do not put the hydrogen which is attached to the carbon. So, that is why the hydrogen is missing. So, the carbon has a hydrogen, has a carboxylic acid, has a wedge, and this whole group. That means, four different groups are attached to this carbon, and these four different groups are attached according to Van 't Hoff and Lowell. They said that they are attached in a tetrahedral fashion, and because of these tetrahedral arrangement, they said that if a carbon has these four different groups attached to it, then you can generate two molecules out of it, and one will be the mirror image of the other, and they can exist as a pair of isomers. So, that is a breakthrough concept. Remember, it is only 1874. At that time, the tetrahedral geometry of carbon via sp3 hybridization was not known. So, it was a pure speculation or a brilliance from these two scientists who could propose the tetrahedral geometry of carbon, because they knew that if the carbon is flat, square planar, then you cannot generate this type of systems out of it. So, just from geometric concept, they developed this tetrahedral geometry of carbon. So, what is the ultimate? So, first it was the development of plane polarized light, then the observation that some molecules rotate the plane of plane polarized light. The third is the tartaric acid story. So, it all started with tartaric acid, and the tartaric acid, existence of tartaric acid in three different forms, and finally, Van 't Hoff and Lowell, they postulated that this is because of the existence of a carbon with four different groups, and you can generate two different molecules out of this. So, that takes care of the slides. Now, I will show you, I will start from Van 't Hoff of Lowell, what they said, I will show you in the model. See, if you look at this system, that there is a carbon, there is a green atom, there is a blue atom, there is a white atom and a red atom. Okay. So, this is the tetrahedral carbon with four different groups, and if you take a mirror image of this, and I can take a mirror image of this, I can build up this molecule. So, they are not mirror images, I think you have to rotate it a little bit. Yes, and now you can see that they are mirror images of each other, but if you now want to see whether they are identical or not, you try to what is called the principle of superposition. So, you want to put one on top of each other and then see whether they are superimposable. That means, all the green atoms or blue atoms or red atoms or the white atoms, they match or they fall on top of one another or not. So, that is what is called superimposition. So, you apply that superimposition principle, Now, whatever you do, if you try to match the green and the blue, you see there is a mismatch between the red and the white. Here also there is a mismatch between the red and the white. If you want to match the red ones and the green ones, now what happens? You see there is a mismatch between the blue and the white. So, basically you cannot superimpose these two molecules. So, they are mirror images, they are different. So, that is the starting point, as I said. So, they are now isomers, because you know what are isomers? Isomers are molecules with the same molecular formula, but having different properties. That means, different molecules with same molecular formula are called isomers. Okay. So, let us start with this. Isomerism is a very important concept in not only in stereochemistry, but also in two dimensional chemistry, we know. And we can now subdivide this isomerism into two classes. One was based on two dimensional chemistry, and that is called, the kind of isomerism that you are exposed to is called constitutional isomerism. Now, what is that? What is constitution? Constitution is nothing but what is called the connectivity. That means, if I have a carbon C, another carbon, it's a 3 carbon system, and then if I have OH here versus again the 3 carbon system, if I have OH here, I am not putting the hydrogens. If you put the hydrogens now, methyl, this is hydrogen, this is methyl, and that is CH2, CH2 and CH3. Now, what is the difference between these two molecules? The difference is in their connectivity. Here the terminal carbon is connected to OH, here the middle carbon is connected to OH. So, that is what that means, they have different constitution. Constitution means the connectivity. So, this is also isomerism, but that will be called constitutional isomerism. So, you have a set of constitutional isomerism. Similar is in constitutional isomerism, you have different branches, you have different subdivisions. These are all known, like one is called chain isomerism, where the carbon chain is different. So, if you have 4 carbon system, you can draw this 4 carbon system in this fashion also. So, again the constitution is different, this is N-butane and this is 2-methyl butane. They are different molecules because their constitution is different. So, but that is called chain isomerism. Then you have positional isomerism, like this example. Positional isomerism, the hydroxy group changes position from here to there. So, that is called positional isomerism. And another class of constitutional isomerism is what is called functional group isomerism. I am not again putting the hydrogens. So, this is a ether molecule. So, this is ethyl methyl ether. You can draw another molecule with the same molecular formula, but that will be called propanol, 1-propanol. Okay. So, that is what is called functional group isomerism. So, you have 3 types: chain isomerism, then positional isomerism, and you have functional group isomerism. But this is 2-dimensional chemistry, again I repeat. The more important one which is relevant to our subject is this, is the other part where the constitution is same, but the molecules are different, and that is called stereoisomerism. So, if the constitution is different, that means connectivity, atom connectivity is different, then they fall into the class of constitutional isomerism. If the connectivity is same, but the molecules are still different, like tartaric acid as I showed, where the connectivities are all same, but you have 3 different types of tartaric acid. So, then the concept of stereoisomerism comes. So, what are stereoisomers then? Molecules with same molecular formula, with same functional groups, with same constitution. So, what is the difference? The difference is the arrangement of the groups in the 3 dimensional space. So, that is they are the stereoisomers. Now, in stereoisomerism you have again 2 different types of stereoisomerism. One is called enantiomerism and the other is called diastereoisomerism. Okay. So, we will discuss, we will start from this stereoisomerism, enantio and diastereo from now on. Okay. Enantiomers are molecules which are mirror images, non superimposable mirror images of each other, like what I showed about the racemic tartaric acid, which was resolved into 2 sets of crystals. One crystal was mirror image of the other crystals, but they are not superimposable, they are different. Similarly, molecules, if you look at the molecular level, molecules which are stereoisomers and mirror images, non superimposable mirror images of each other, they are called enantiomers. Whereas, molecules which have same constitution, same functional groups, same connectivity, but they are not mirror images of each other, and they are called diastereomers, or you can say the molecules are exhibiting diastereoisomerism. Okay. Okay, let us wipe this out now. Let us concentrate on the first on the enantiomerism. So, enantiomers are what? Enantiomers, again I repeat, are molecules which are non superimposable, are stereoisomers which are non superimposable on each other, which are non superimposable mirror images of each other. They are called enantiomers, and they have the typical property of rotating the plane of plane polarized light. So, if you take an enantiomer means always a pair, enantiomeric pair. So, one is the mirror image of the other. So, if I have I have a mirror image of A. If this has got a plus rotation, so I can have a mirror image which will have a minus rotation. So, they are a pair of enantiomers. Okay. So, enantiomerism is directly connected to optical activity. So, if you take just one enantiomer and pass the light, this light will be rotated clockwise or anti-clockwise direction. One thing one should remember, that this rotation, when we tell, we have to view the rotation from against the propagation of the light. So, if light moves from here to there, the observer is here, the observer's eye should be here, and then he will see whether it is rotating clockwise or anti-clockwise. This is very important, because if you look from this side, then the clockwise becomes anti-clockwise and the anti-clockwise becomes clockwise. So, basically what, when the chemists measure the optical rotation of a molecule, what is optical rotation? That means the degree of rotation that what the molecule does onto the plane of plane polarized light. So, you have to view against the propagation of the light. Okay. Then you can say that whether it is clockwise rotation or it is anti-clockwise rotation. Now, by the way, clockwise rotation is also called dextro, as I already mentioned, dextro-rotatory molecule. If a molecule rotates the plane of plane polarized light in the clockwise direction, that is called dextro-rotatory molecule, and the other one will be called levorotatory, that means levorotatory molecules rotate the plane of plane polarized light into the left side. The question is, we know that they form a superimposable mirror image, a non superimposable mirror image, sorry, they form a non superimposable mirror image system. But what makes it, or what is the cause of this rotation, what is the genesis of this optical activity? Okay. Now, by the way, another terminology is there, that molecules which can rotate the plane of plane polarized light, they are called, earlier I said they are optically active compounds, they are also called chiral molecules. Okay. Chiral molecules, like these two hands, one hand is the mirror image of the other. So, but they are not superimposable, as I said, and this is hand. So, if I consider this as a molecule, so if light passes through this, the light will suffer rotation. If light passes through this, that will also suffer rotation, but the two rotations will be just opposite to each other. Okay. This is, earlier it used to be called handedness, but that same thing is the modern day we call it chirality. Okay. So, now we can summarize a little bit, that what we have learned is that there are molecules which have the same molecular formula, same connectivity, same functional group, but they can be different. They are called stereoisomerism, and that stereoisomerism is arising because of the disposition, different disposition of groups in the three dimensional space. Then we have seen that there are two sets of stereoisomers, one is called enantiomers and the other set is called diastereomers. Enantiomers are non superimposable mirror images, and diastereomers are, they are not mirror images of each other, but they are stereoisomers. Okay. Then enantiomers have the property of rotating the plane of plane polarized light. I am not concentrating, we will come back to the diastereomer later on, but let us first concentrate on the enantiomer, that enantiomers have the capability, because they are chiral, they have the capability of rotating the plane of plane polarized light. Now comes the bigger issue, that why these molecules which have non-resolvable or which have non-superimposable mirror images, why do they rotate the plane of plane polarized light? Okay. So, that will be the next half an hour, we will discuss the genesis of this optical activity.